Just okay. Just so you know, it is really warm in this thing, and I don't think the hood will stay on the whole time. I mean, like you might get 5 minutes if you're lucky here. Probably doesn't help that I'm drinking hot tea. Okay. Woo. All right. Last day of class for Math 225. Let me move that window there. This window there. I can barely see right now. Okay. Yeah. Let's see. So, I'd like to start. Oh yeah, just announcements, right? Homework due today. Pre-final math as a process thing. Please turn that in Monday, unless you need later. Just let me know. I will be posting some practice materials and doing some grading and all that stuff. So the practice materials, I think, is the first priority. I will be working on that today and try to post tonight, maybe tomorrow morning. Um, and let's just dig into some practice stuff. So give a combinatorial proof. Oh my goodness, it's getting hot already. I'm like, glasses are fogging up. We're gonna see how long this goes here. And so give it a combinatorial proof of n choose k is equal to n choose n minus k, where as part of this problem, n has to be greater than or equal to k. So first of all, here's not an answer. I mean, there's still something relevant in what we're about to say here, but just maybe as a reminder that n choose k was defined, right? So this was actually had formula. Like, what does this thing break down into? This was n factorial over k factorial times n minus k factorial. Okay, so that would be the left side, right? In fact, using the same formula, the right side, n choose n minus k. Now here's the thing. You've got to take a look at the formula that was just mentioned right here, like what the binomial coefficient turns into, and plug in n for n and plug in n minus k for the k, and you'll have n factorial over, there's a k where we need to now plug in, I can barely see, okay, where we need to plug in n minus k for that k. So n minus k quantity factorial times n minus, and then there's a k for which we need to plug in n minus k. So n minus k close parentheses, factorial. This is n factorial over n minus k quantity factorial. Here, if you distribute that minus n plus k quantity factorial equals n factorial over n minus k factorial. N minus n's cancel out there. So look, other than the two things that are multiplied together in the denominator being swapped, we can see that these are the same, right? So this is a proof, it's just not a combinatorial proof. In fact, to clarify what's going on here, let me say that this is an algebraic proof. This is an algebraic proof of n choose k equals n choose n minus k. Okay, this is not a combinatorial proof. Right? So oh my goodness, I can't. So is this a proof? Yeah, it's a proof, but it's just, if the question said give a combinatorial proof, and you give this algebraic proof, it doesn't really answer the question, right? Like I mean, it's something, but it's not a combinatorial proof. So I'd like to reprove this. I'd like to give an answer that is a combinatorial proof, meaning we should come up with a counting question, right? So we need to come up with a counting question. And here's what I'd like to do. Let's say you have, I don't know, n index cards. So there are these n index cards, and you just label them 1, 2, 3, 4, 5, all the way up to n. Labeled 1, 2, 3, so on and so forth, dot, 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 until you get up to n. And then let's say you have two bins. Like a red bin and a blue bin. I don't know, red bin, blue bin. And for this game, let's say, right, for this counting problem, let's say you have to put k of these cards, k of the cards. There are n cards total, but you have to put k of the cards, k of these n cards, in the red bin, and the rest in the blue bin. Okay, all right. And then I guess to really, I haven't been doing a great job of making the counting question a counting question and stating the question, but I have it in my notes. Let me just say, how many ways are there to do this? So to address the left side of this identity or this equation up here, the left side. So you have to pick or choose, right? So you pick k of the n cards to put in the red bin. And just we should note that there are n choose k ways of doing this. And then the rest of the cards, the rest go in the blue bin. At this point, there are no choices to make. The rest of them go in the blue bin. So in total, there's n choose k ways to do this. To address the right side, that is, so we've answered the counting question, but we're gonna now ignore the work that we just did here. And to re-answer the counting question again, you could say, how about you pick n minus k of the n cards. Oh my goodness. N cards to put in the blue bin. So out of n cards total, you're going to pick n minus k of them or choose n minus k of them. There's n choose n minus k ways to do this. And then the rest, there's no choices left, right? Nothing to choose anymore. It's automatic. The rest of the cards, the unchosen cards, go in the red bin. And if you just do the arithmetic, k of the cards end up in the red bin, as should have occurred. Okay, so that's there we go. We're done. Box. That's the combinatorial proof here. Okay, I think I need to. Yeah, excited for summer. Well, just be doing some research and probably prepping classes for maybe some online stuff. All right, let's just. Okay, here. So let's see how we're doing timing wise. Yeah, okay. Well, I just I need to comment. Like we discussed it yesterday, and I wanted to say more. But like, if you know that A is a subset of B, you don't want to write let X belong to A, right? Unless you have another reason to write it. But like this to me sounds like someone's proving A is a subset of B. This sounds like proving A is a subset of B, right? If you already know A is a subset of B, why start a proof of A is a subset of B, right? You already know it. Well, you'd be wasting time proving a thing you already know, and maybe more importantly, you probably don't have the ingredients to prove it. So I think sometimes what happens in 225 is that people introduce additional assumptions that aren't allowed. Like there are certain times that you're allowed to do a let da 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 da, right? Like there. So I tried to think of all of them. I probably forgot something, but I just name all the situations when you would write let X belong to A. I think it's good right now, as a last day thing to just let's make sure we have some clarity about so first of all, one situation would be when you're proving that A is a subset of something, squiggle. Okay? A second situation would be when you're proving a statement that starts for all whatever in A, whatever, right? So that's another time you would do, let X belong to A. A third situation I could think of, now we're just really digging into okay, well, technically, if you're proving an if then, that looks like this. If X is an A, then something, right? So then, to prove an if then, typically you assume the if part and prove the then part instead of doing, at least for the direct proof. On the other hand, if you know, let's just put this on the top of the next page. If you know, now I'm changing it up, new situation. If you already know that X belongs to A, then what other statement would you be looking for so that you can combine the two to get something new? Well, so let's say, the point is, let's say you already know X belongs to A. And then if you know some other thing, then you can combine the two things and get a new conclusion, right? So this is a bit in a cartoon fashion, but like, let's say you already know x belongs to a, then maybe if you know either because it was provided as a hypothesis or you just proved it to be true, and you know for all blah in a something, then these two things could combine to give you that text that's here, although some replacement of variables, which is why this is a little bit like a cartoon. But like, when I know that I have a thing inside an element, like maybe called little x or whatever, belonging to a set A, one of the things I'm looking for is, do I already know a for all statement regarding that set? Do I already know such a statement being true? That's one time you might be using x belongs to A, right? It's like like you have this information that x belongs to A. I'm just trying to say that my habit is thinking about like, where's an opportunity where we can actually use that. So just to give you a second scenario, if you know x belongs to A, maybe you also know, again, not proving right now, like let's say you know that if x belongs to A, then something. Maybe you already know this implication is true. Well then, modus ponens, right? So you get to conclude the part that's there in the squiggle. Let me call that 2a because there'd be a 2b, right? If you know x belongs to a, I mean, we're really digging into just all the possibilities that I could think of. Anyway, like I'm probably missing something, but if blah, then x doesn't belong to a, right? So if you have if you have the negation of the conclusion right here, because this is x doesn't belong to A is the opposite of x belongs to A, then here you would conclude the negation of the if part, right? This is modus tollens. Okay, I'm just like really trying to dig into all the possibilities I could think of. As a third, so that was 2a, 2b. I guess maybe this is technically the fourth one, but like let's say you had this. If A is defined for you, like you're told how the set looks, like you're told that A is defined as A equals y and c satisfying something here, some condition here that mentions y in it. Then if you know x is in A, then you can get two things. You get x is in C, and you get this statement that's over here with the squiggle is just replacing all the y's with x's. Again, this is a bit of a cartoon. And then one last one, if x is in A and okay, x is, I better make that really look like a membership symbol here. So x is in A and A is a subset of B, then these things would combine to give you x is in B. Right? So, I mean, this is, again, I'm just pulling lots of different ideas and bringing up many different hypothetical situations here, but you want to be very careful about when bringing up assumptions just willy-nilly isn't a good idea. It doesn't work. And then if you know something, I mean, that's been sort of one of the features, I think, of this class that maybe you've noticed that if you know something to be true, sometimes that one thing, like here, provides two other facts immediately. Other times, for that to be useful, you've got to like look for another statement. So like, what's a relevant statement? Like that's a thing to be thinking of, and that's kind of a place where people often do get stuck. So just things to think about for whenever you're stuck in a proof. So today, the main thing I want to do with the remaining 41 minutes is work on a rather long two-part proof, if that's okay with you. Challenging question, perhaps, but like it just nothing strictly speaking new. It's just good chance to review lots of things. So let V be the set of all functions. You may want to write down some of these sets will keep reappearing. So capital D. I will write D sometimes. I'll write out what D is. Let me just define. D is just the set of numbers 1, 2, 3. Just those three integers. To C. And for C, I mean the set of reals. Okay. So V is a set of all functions whose domain is 1, 2, 3, and codomain is reals. And as part of this question, if little u, little v belong to capital V, then we define u star v. I'm defining what star is to be the following. So u star v is defined to be the sum I from 1 to 3 of u of I, v of I. And then this two-part question, so part A, is let tilde be the relation on V defined by U tilde V if U star V is greater than or equal to 0. And okay, so an additional thing was defined in part A here, and then the task here is to prove that this tilde is reflexive. And then part B uses this tilde. So in part B, let capital A equal the set little u in capital V, satisfying for all little I in D. That's the same capital D up here, right? So every time you see a letter, it has the same meaning. For all little I in D, u of I is greater than or equal to 0. And we're also going to define, so let capital B equal the set of all V in capital V, satisfying for all W in capital A. Oh my goodness. For all W in capital A, V tilde W. So that tilde is the one that was defined in the previous part. So there's this. And then part B is to prove that A is equal to B. Sounds like a lot, right? There's a lot of things that are going to be going on here, but I think this will be a nice little problem. A couple comments. First of all, this defined by, like, as with any other definition, this is defined to be that. So these two things circled in blue, you can switch them for each other. So U tilde V is the same as U star V greater than or equal to 0. J tilde K would be the same as J star K greater than or equal to 0. Now we could just dig into the proof, but I think one of the things I'm trying to convince you of, and I hope you were somewhat convinced of this yesterday, is that it's good to build intuition. Build intuition for what's going on. Because take a look, even in the beginning here, right? It says it's talking. There's this V is a set of some kind of functions, and then if you have little u and little v that belong to capital V, then you define this U star V thing. All kinds of things are happening, and it'd be good to practice. I would say, to practice what U star V is, U star V, by making, first of all, by making a little u in capital V and a little v in capital V, because those are the ingredients necessary in order to really dig into this U star V, right? So let me do that, right? Like I'm gonna just define for you, like if this requires little u has to be in capital V, and capital V is a set of all functions from D to C, then little u needs to be a specific function from D to C. So I'm going to define little u to be a function from D. I just wrote it out, 1, 2, 3. I could have written a capital D instead of the curly brace business here. To reals with a rule. So I'm just making a function. I'm just really making a function with domain of cardinality 3, codomain, any real number, right? So one way to write down the rule for the function, just as a reminder, is I could write ordered pairs. So ordered pair 1, 6, ordered pair 2, 0, ordered pair 3, -8. I hope, does that work for everyone? Like that defines, I just defined a little u. Just so defined this way, little u belongs to capital V, because V is a set of all functions with domain 1, 2, 3 and codomain reals. So this is one of them. I just made something up, right? And then how about I'll define little v also from set 1, 2, 3 to reals. I could have written here just a D and a C, but I just wrote it out here like this. And then with rule, and just to for the sake of review day, like just write, I want to write the rule differently. I'm just going to write v of 1 equals pi, and v of 2 equals 11, and v of 3 is equal to 4. Yeah, so little v belongs to capital V, right? It's a function where the domain is the set 1, 2, 3, and the codomain is reals. Every output is a real number. And actually, moreover, let's just take a look at how capital A was defined. A was functions, right? So A is a set of functions, because the elements that belong to capital A need to belong to capital V. But functions where for each thing in the domain, for each of 1, 2, and 3, the output needs to be bigger than or equal to 0. And that's actually something that happens with v here. So this v defined here actually belongs to capital A. Just comment. Okay. So look, I want to practice this u star v definition. It was defined as the sum I from 1 to 3 of u of I, v of I. And let's just write this out, right? Just write out what the sigma notation means, because sometimes that's the abstract part. So u of 1 times v of 1 plus u of 2 times v of 2 plus u of 3 times v of 3 times, let's try that again, v of 3. Okay, so, well, u of 1, so that's 6, right? V of 1 is pi, u of 2, so plus u of 2 times v of 2. So 0 times 11 plus, and then u of 3 times v of 3. So negative 8 times 4. Okay, this ends up simplifying to 6 pi minus 32. Right? The middle term, 0 times whatever, just goes away. 0 times whatever. So the whole point is what we learned, I hope, in this process. We learned the key thing to notice is that if little u and little v belong to capital V, what is this u star v thingy? Well, look, we got here 6 pi minus 32. That's a number, right? U star v is a real number. It's good to keep in mind that u star v is a number. So you start with two functions, and this star procedure creates a real number out of it. We doing okay so far? So as a remark, this is something for like if you took Calc 2 or linear algebra, either took or are taking. I want you to just like, again, if those are not courses you've taken, don't stress about this too much. I just want to show a connection is all. So just as a remark, consider the three-dimensional vectors. And I'll use kind of typical vector notation, a little u with an arrow above it. 6 comma 0 comma negative 8, and a vector v. Let's see, what do I have here? Pi 11 4. You know, these are both in R3. I think typically in linear algebra, this kind of notation r to the 3 like that is used. We actually did mention this in this class as well. So when you have a set raised to an exponent, that's actually just multiple Cartesian product. So just creating the connections here, right? Then if you're familiar with some vector-y things, there's this thing called the dot product for two vectors, and that should just be multiplying corresponding, so 6 times pi plus 0 times 11 plus negative 8 times 4, right? And my question, I guess, is like, how different is this? Than earlier, I mean, I had a u and a v without arrows, so I'm considering those different things, right? So how different is this than this u star v that we computed earlier? It's not. I mean, in terms of the actual computation and the number that we get and the arithmetic that was involved, it's the same. These are different objects. Over here, at the bottom of the previous page, u and v are functions, whereas over here, this u arrow v arrow, those are vectors. So there are actual technical differences, but for what the things are. But this u star v that's happening up here, it's not morally all that different from a dot product, right? It's sort of like I defined a dot product for functions, kind of, in a sense. That's all that really happened here. Okay, so with that kind of intuitive side of things discussed, let's prove part A. And again, you don't have to, strictly speaking, go through that intuitive exploration thing, but I think it's very hard to work on proofs if you don't know what objects you're really dealing with. So part A, just as a reminder, we want to prove that tilde defined on V so it's tilde on V. It's a relation on V, and it was defined by u tilde V if, just reminding you from up there, u star V greater than or equal to 0. Okay, so that's how tilde was defined, and then we want to prove that this tilde is reflexive. Okay, so let me just say then the following, right? Like tilde on V is reflexive. We've seen phrasing like this when we first looked at relations. And based on how tilde is defined here, like in this problem, U tilde V is defined as U star V greater than or equal to 0, right? Now that's going to come up in a moment, but what I want to do is just take a talk about what reflexive just is in general. And I remind you that in the definition, if you just look it up, it's like for all things belonging to this set here, that thing tilde itself ends up being true, right? These two boxes of text to me are the same. What I'm trying to say is the definition, the definition allows you to go back and forth, right? Even though the first time the word if appears in a definition, it's really if. It operates like an if and only if. So this box turns into that box turns into this. That's all that's really happening with definitions, right? Like it's a huge theme for the semester. And the point is, if we need to prove this, which is right, like we need to prove that's what the task is up here, then it's the same to just prove this instead. That's all that's going, like that's so many definitions that we have seen post spring break. Basically, right after that if, start with a quantifier, like a for all. And so we just go back then to things pre-spring break and just do what we need to do to prove a for all. And that's what post 225 classes are about a lot, right? It's this idea of, look, this definition starts with a for all, so proving this is the same as proving that. And how do we prove a for all? Right? We know that what we should do is let little a belong to V, right? Be arbitrary. And we want to show then this part here. We want to show a tilde a. And if we translate what that means, so go back up here. So U tilde V translates to U star V greater than or equal to 0. In other words, what we want to show is a star a greater than or equal to 0. All I did was I took the two pieces of blue text and plugged in little a for both little u and little v. That's all we want to do here, right? By the way, the fact that little a belongs to capital V, if you go back and look at what V was, remember V was defined as a set of all functions from D to C. So little a is a function from D, I'm writing it out, to C, and C was the set of reals. That's what we know about little a. A is a function with domain 1, 2, 3 and codomain reals. That's all we know. And then we want to show this. Well, how are we going to do that? I'll just say let's start with the left side. Let's just start with this a star a business. And remember how a star a was defined. It was like a dot product, right? Morally like a dot product. And just we can go back and look up the definition. It was a sum, I from 1 to 3, of a of I, a of I. If you want to write it out, without writing sigma notation, fine. A of 1 times a of 1 plus a of 2 times a of 2 plus a of 3 times a of 3. And if we think about this, look, it's a of 1 is a real number, right? It's a thing that belongs to R. A real number times itself. What do we know about that? What can we say about a real number times itself? Drink some tea. See if we get a response. Real number times itself. Can we say that a real number times itself should be bigger than or equal to 0, right? So this right here is greater than or equal to 0. Take any real number, take negative 8, square it, multiply it by itself, you get a number that's greater than or equal to 0. Same deal here. This is greater than or equal to 0. Right? A3 times A3 is greater than or equal to 0. So if we add three things that are greater than or equal to 0, we have something that's greater than or equal to 0. Right? So a star a is bigger than or equal to 0, which is the thing we wanted to show here. That does the proof of tilde is reflexive. Right? I mean, if I have slightly more detail to just I've written up, but like so a tilde a, okay, and then does that look okay? Questions about part A? I want to do the part B proof, but I want to just make sure we have any questions that I can address for part A. Okay, let's take a look at part B. In part B, just as a reminder, maybe you already have this, but I'll just write it here so we don't have to scroll too far. Capital A was defined as the set of U's in capital V satisfying every output was bigger than or equal to 0. So the way it was written was for all I in D, U of I greater than or equal to 0. So D isn't so huge, right? Just 3 elements, but it's like another way to say this would have been U of 1 bigger than or equal to 0, U of 2 bigger than or equal to 0, and U of 3 bigger than or equal to 0. B was defined up there in the question as V in capital V, satisfying for all W in A, V tilde W. Okay, and then the task here was to prove that A is equal to B. Now, the thing to note, right, is that A and B are sets, right, because of the curly braces. So, not that this text is part of the proof, but I think this is good right now as a reminder that A and B are sets. Sets of what? They're actually sets of functions, aren't they? Right? Because look, the thingies have to belong to capital V in order to belong to either A or to B. So A is a set of functions. I mean, you'll note here, like right away, just due to the fact that to belong to A, thing has to belong to capital V. Capital A is a subset of V. Capital B is a subset of V. So A is a set, since V is a set of functions, A is a set of functions. B is a set of functions as well. And where the domain is D and the codomain is C and all that, right? So look, the point is, since A and B are sets, how do you prove A equals B? You always want to talk about that first, right? Because proving functions are equal and proving sets are equal have different processes. So since these are sets, by definition of what it means for sets to be equal, we need to prove A is a subset of B, and we need to prove B is a subset of A. So let's do that. Let's do a proof of A is a subset of B first. Okay, so to prove A is a subset of B, we need to pick an element of A. So I'm going to call that element U. So let U be an element of capital A. We want to show U is an element of B, right? So, I mean, again, just all the usual habits here, right? Now here's the thing: since the little u belongs to A, we have these things being true, right? So what we have, so we have little u belongs to V, and we have for all I in D, U of I is greater than or equal to 0. And just, I put this note here in blue in my own notes. You can look at later, but I'll just write this in, that what this is, again, I think I already said it, but what's going on here is that we're talking about, this is a function with all 3 of its outputs, all 3 outputs. There's only 3 outputs because there's only 3 inputs, right? So all 3 outputs are greater than or equal to 0. And that's all this for all is really saying. Okay, and then remember let's take a look at what we want. We want U to belong to B. That's what we said over here. We want to show U belongs to B. But take a look at how B is defined. Right, so this V that appears here is a placeholder variable. We've got to place in there right now, we should place in there this U, right? So what we really ultimately want is we want U to be in V. I'm looking at this, just replacing the little v with a little u. And we want for all W in A, U tilde W. Right? That's just looking at the definition of B. That's what we want. That's what we need to have be true. Now, one of those, this U belonging to V part, Done. We already know that because that just it's like literally right above. Okay. The thing that we need to have true is this, right? So we need to prove this. Fair? Because we want to show, we want it to be true, so we need to prove it. But take a look. The thing we need to prove starts with a for all. So we should pick something arbitrary in this set, capital A. You can name it anything you want other than little u, I guess, right? So I'm going to just name it W. I think that'll work for us. So to prove this, is there a comment? No, there wasn't. I was just, okay. So to prove this, we should let W belong to capital A, right? And what we want to show then is this text here. We want to show U tilde W. And if we just break apart what this tilde means, let's just recall. I know it's been a little while, but recall then what we want to show. To translate this U tilde W, it's that we want U star W to be bigger than or equal to 0. That's what we want. Now here's the thing. We have W belongs to capital A. We haven't done anything with that. But just like U belonging to A translated into these two facts. Uh-oh. There we go. There we go. Since U belonging to A translated into two facts, in the same way, W belonging to A translates to the same two facts, right? So we get W belongs to V, and we also get for all I in D, W of I is greater than or equal to 0. Just what happens for something belonging to capital A due to how the set A was defined. Now, we want to show, I mean, it's written in a couple different ways. We want to show this, but we've written it this way because at least we peel apart this language of tilde. Like tilde was this extra layer of definition, and we peel apart that layer. We want then U star W to be greater than or equal to 0. So let's work with the left side of that. So U star W. Okay, U star W, it's, if you go back, it was this sigma notation thingy, but remember, it's like morally, it's like a dot product. What we really have going on is U of 1 times W of 1 plus U of 2 times W of 2 plus U of 3 times W of 3. Now we want that to be bigger than or equal to 0. Well, what are we going to do? Take a look at what we have up here. Right? Over here we said that every output of U is bigger than or equal to 0. Right? For all I in 1, 2, 3, this D, remember, was 1, 2, 3. U of I is greater than or equal to 0. So what we're being told that U of 1 is bigger than or equal to 0, U of 2 is bigger than or equal to 0, and U of 3 is bigger than or equal to 0. Now what? I'll drink some tea. And Olaf will melt. Actually, this tea is probably cold now. So, anybody want to share a thought? What else do we do? We're trying to prove that this expression is bigger than or equal to 0. Is there a fact we haven't used yet? Yeah, use that W's in A, right? So that W's in A, we got this, but more importantly, we got this thing. I mean, not box, it's probably visually distracting. So we also have the same sort of fact for the function little w. So, right, we have that this output is greater than or equal to 0, and this output is greater than or equal to 0, and this output is greater than or equal to 0. And think about it. You multiply two things that are greater than or equal to 0, you get a greater than or equal to 0. Two reals that are greater than or equal to 0 multiplied together, that's going to be greater than or equal to 0. This is greater than or equal to 0. You add things that are all greater than or equal to 0, and you get a greater than or equal to 0. So this final want to show, check, we have it. So this is a proof that A is a subset of B. Okay, I'm gonna. I have two proofs in the notes, in my notes, that I hope I uploaded. If I've forgotten, somebody remind me. I'll upload it. I want to actually do the second proof that I have of B is a subset of A. Oh, come on. Oh, no. There we go. Okay. So I have two totally different proofs of B is a subset of A in the notes. I'm going to do the second proof that I have. Just the first proof's got some strange feature. I mean, this one has some strange features too, don't get me wrong. But let something belong to capital B. I just happen to name it little b. I'll follow the same notation I have in my notes. And we want to show that same creature, the same little b, belongs to capital A, right? Usual outline, usual setup of a proof of subsets. Now, the fact that something belongs to B, maybe, sorry, I'm going to just, let me just copy, paste this almost for myself, kind of down here so that I can kind of see it. In fact, let me just reorganize a couple things. Sorry, that's part of being online, I guess, right? So there was our up to there was our finishing of the proof of A is a subset of B. Let's just put that there for reference. Maybe that'll help me out anyway a little bit. Even though I'm following my notes on another screen, just at least being able to point to a little bit will be helpful here. Okay, so the fact that we're starting with little b belongs to capital B, and the way this is defined, we get two facts over here underlined. We just need to replace the placeholder little v's with little b's instead, right? So we get here that little b belongs to V, and we have for all W in A, B tilde W, right? We're not trying to prove this fact. We know that. I mean, it follows the word so. It's a fact we know. So as I see this for all W and A, and it's like I want to use this fact. In order to use this fact, I need something that belongs to capital A. We don't have one right now, but that's what I want to do, right? By the way, this fact that we know, I'm going to translate it. So another way to say this is, let me copy the quantified part here for all W and A, but I just want to translate this tilde because it's another layer of definition, and each time you can peel apart that definition, it helps. Remember that one thing tilde another meant that if you star the two things together, which this is kind of morally like a dot product, the number you end up getting is greater than or equal to 0. So this is just restating, it's just translating what's in this box just by unpacking what this tilde meant. All right. So again, we're not trying to prove this box statement either. It's a statement we know. We're looking for an opportunity to use this fact, but to use this fact, you need to have an element of capital A. We don't have one yet. All right. And we want to show, so thinking about how we want to show B belongs to capital A, so take a look. These two parts, let me maybe use a new color here. These two parts over here, underlined in red, we want those to be true, replacing the placeholder u's with little b's, right? So what we want to show is that B belongs to V. That's the first underlined red part. And we also want to show for all I in D, oh yeah, this is a placeholder U. So we for all I in D, B of I is greater than or equal to 0. That's what we want to show. The first part, this thing that we want to show, check. There's nothing to show because we already knew that B belongs to V. That came about as one of the two facts from little b belonging to capital B. So the harder part is to show this. We want to show that. Right? So to prove this, again, we're proving a statement that starts for all. So, usual thing, right? To prove this, let little I belong to D. And here, I think it's helpful as a reminder that capital D was a set of cardinality 3, specifically this set of cardinality 3, just 1, 2, 3, right? And we want to show B of I is greater than or equal to 0. Now, I have this note, and I think it'll be rather helpful right now to mention that when we write let little I belong to D, what's going on in the proof is that the person reading the proof, the reader, has chosen I. they've chosen little I to be, well, an element of capital D, but there's only three choices. We don't know what their choice is, but so they've chosen little I to be 1 or 2 or 3. We don't know which, right? But it's fixed, but we don't know. The choice is fixed, but we don't know which. Okay? So I might be 1, I might be 2, or I might be 3. It's not all three of them. Like, we're just making the reader pick one, and if they want to, they read our proof, they don't buy the argument, they can, because they're worried we cheated with the for all business, they could rewind the story back to this point and pick a different I, but whatever I they pick, they've got to like follow that through for the rest of the proof. So I is a fixed thing. What I'm saying is, in other places earlier, sorry for the scrolling, earlier, like in how this was defined over here, I was an index variable, and so I was playing more the role of a variable over there. Just right here, I is now fixed. Okay, we wrote let I belong to capital D, so I is fixed. If you don't like the fact that, I mean, the only reason there's an I here is because I just copied the variable I there. If you don't like this, you can change the little I to a different variable for the rest of this proof. But just please note that right now I is fixed. I'm going to define a function. I'm going to define, and this function looks a little peculiar, why I'm defining it this way. And the insight behind defining this function this way is actually in the other proof of B is a subset of A, which we're not covering because it's a little weirder, I guess. But let me just define a function, and this looks out of nowhere, as sometimes some of the things defined do, right? But I'm going to define a function from the set D to the set C, just written as 1, 2, 3 to the set of reals, by the rule. And f of, I was going to use an I here, and I noticed in my own notes as I was trying to write this, I put an I, like, that doesn't make sense. I is fixed. So I'm going to use an N here. If my pen would behave. Uh-oh, this is not good. Okay, let's see. Nope, that's not good. There we go. Just had to reset the battery or something. So f of n, piecewise, is going to be, I just picked a number, 225. It's a good number, right? If n is equal to I. So if the input is the number that the reader picked earlier, so if the reader picked 2, then I'm saying f of 2 will have output 225. Otherwise, all the other outputs are going to be 0. So it looks really peculiar, but this technically defines a function. Again, I is fixed. So this function should have 3 outputs, right? There's 3 inputs. You got to pick 3 outputs. Of course, you can repeat an output if you want. One of the outputs is 225, and the other 2 outputs are 0. So this is not an injective function. I don't care, but it is a function where one output is 225. For which one of these inputs is the output 225? I don't know. It's to refer to it. It's based on what the reader selected to be I. Okay, so this does define a function where one output is 225 and then the other 2 outputs are 0. The output that's 225 is when the input is what the reader picked. Here's the thing though. Based on how I've defined the function, I want you to notice that the way I define the function, since f of 1 is greater than or equal to 0, and f of 2 is greater than or equal to 0, and f of 3 is greater than or equal to 0, right? Because all of the possible outputs are either a 225 or a 0. So f of 1, f of 2, f of 3, they're all greater than or equal to 0. What we actually have here is little f belongs to capital A. I remind you a long time ago that capital A was a set of all these functions where the output's always greater than or equal to 0. So what does that do for us? Well, way back when we had this statement over here, it's true. Over here, this box statement is not one we're trying to prove, it's one we know to be true. So if you know of something in A, which I created one for you here, you actually get, we're using this for all, we get B star F is greater than or equal to 0. Well, what's B star F? B star F is b of 1. So let's just write it this way. I'm going to actually use the sigma notation. It'll actually help us out. It's the sum n going from 1. I couldn't use an I because I is fixed. The sum n going from 1 to 3 of b of n times f of n. Now here's the thing. F of n is 0 most of the time. It's 0 unless n is equal to I. So of this 3-term sum, you get zeros at least twice. One time when you're looking at index I, when n is the index n happens to equal I, then you would get a non-zero value. You get b of I times f of I. But here's the thing about f of I. F of I is by the part by the piece. It's 225. So this is b of I times the number 225. Now here's the thing. What we have here is that b star f turned into this, and b star f is greater than or equal to 0. Well, if b star f simplified to become this, then this thingy here, b of I times 225, this is greater than or equal to 0. Let me try this again. This circled thing in green, it's equal to that. So this right here, also in green, if that's greater than or equal to 0, all the things in green are the same. So this thingy is greater than or equal to 0. And we have this inequality. I'm going to divide both sides, and the good thing I'm dividing by a positive number on both sides. You can't divide by 0, and if you divide by negative, you got to switch the alligator. But I'm going to divide both sides by 225 and get b of I is greater than or equal to 0. And that, by the way, still up here was what we wanted to show. It was our final want to show. So check, we're done. I know it's kind of a bizarre proof. Maybe you want to revisit it or something, right? Like it's a strange one for sure. And if you're just curious or you want sort of a linear algebra perspective on this, think about what this statement says geometrically in linear algebra. That's kind of fun, but not for us, not here not right now. Would cases ever be used for the function you defined? Yeah, so that would have been another option. I appreciate the question. Another way to do this is, like over here, and I erased the comment because I was running out of room. We could have actually, this is totally, not totally different way, but like from this point onward, we could have written this differently where you don't have, instead of doing a piecewise function like I did here, which was sort of like a compact way to do things, you could have instead said either I equals 1 or I equals 2 or I equals 3. Case 1, I equals 1. And then define a function f in that case to be f of 1 equals 225 and f of 2 and f of 3 are both 0. And then run the same argument basically. And then in case 2, you define your function f differently, where f of 2 is 225 and f of 1 and f of 3 are both 0. So this could have been written as a proof by cases so that you don't need a piecewise function. But you're just sort of, the piecewise is sort of just hiding the cases in a sense. So yeah, but yeah, you could do this, you could have done this as a proof by case. It was either do it as a proof by cases or write a piecewise function. And somehow those are like morally achieving the same effect in some sense. Hey, I guess I want to say, if you want to look at the other proof of B is a subset of A, go for it. This is a really funky proof to be fair. But like, again, what I'm just trying to do is I thought like it'd be good to show you some of these things. And I do want to post a lot of practice problems that are not as challenging, like kind of, easier, mid-level, challenging. Like, so I'm working on that and I will get that posted. But I think I have 1 minute and I should just say thank you. I know that this has not been an easy semester or just an easy life or whatever, just how things have been. And I appreciate how hard you have worked. You've shown me that in the process, in your process of doing things, and I'm very thankful. So thanks for letting me, do this, for working through this with me in this strange. If you need anything, just reach out. Whether it's math over the next week or so, and you want office hours at a different time, just send me an email. Or even if you have non-math things come up or after the semester, I'm here for you. I'm on your side. I want you to succeed in what's going on. And okay, I think just as I have in my notes, I'll just say the following about this class. I think it's a challenging class, and um, if I can really identify the two things that make this class what it is, it's the keys to success are definitions and the methods of proof, right? If you just apply those things very consistently, very methodically, that's the class in a nutshell. I've heard in previous semesters students say the following about 225. So you can agree with the statement or not. I definitely agree with what my former students have said about the course. They say that 225 really makes you think about the logic of math, and that you really have to know what you're doing. Like, you can sort of kind of get by in calculus without like, just take a derivative. Don't even think about it. It's the slope of a tangent line or whatever. But like 225, I think it really, and not that I tried to design it that way, but just the nature of the content, like you really have to know what's happening. Again, thank you all. Take care of yourselves, stay healthy, and see you in office hours. Question came up here. Homework 5. Are they moving one unit at a time until they reach an edge? They're moving at so they're moving along the edges. They're moving along the line segments. But yeah, one unit at a time. So take a look at the our class day on counting by bijections that we did last week. I want to say it was last week on Wednesday. Yep. Yeah, you're welcome. Okay, I'll stop the recording.